Okay, hi everybody. My name is Kaitlyn Loftus. I'm a lead postdoc at Columbia working on the warm microphysics project. And today I'm going to talk about using Bayesian statistics and machine learning to constrain parameters in cloud microphysics parameterizations. And of course, I want to acknowledge my many co-authors, collaborators here, including Marcus Van Leeuwenhoek, who's here, and Aziz, who just spoke. So first, I just want to kind of motivate why we're studying clouds. Clouds are a critical component of the climate system because they regulate precipitation, they drive really strong warming and cooling effects relative to I don't really know.
Want to maybe try again?
Sorry, maybe I'll just make them as PDF. I don't know.
Just
Maybe you try again? Yeah. Yeah.
No? Okay.
Yeah.
Okay, great. Yeah, so going back to why are clouds important, they are driving really strong warming and cooling effects relative to changes from anthropogenic CO2. They also are influencing the distribution of water vapor, which is a key greenhouse gas. And they also have interactions with airborne pollutants with consequences for kind of temperature and precipitation. And a key element of clouds is that they have structure from global to micro scales, and that makes them hard to model. And so here we're focused on the kind of micro or particle scale behavior of clouds. And basically every climate model has to parameterize the behavior of individual cloud drops because computationally, it's not tractable for us to kind of model the behavior of every individual particle when a given, say, handful of cloud has maybe billions or trillions of particles in it. And when we think about parameterizations, we can kind of think of two elements of parameterization design. First, we have structure, and then we also have parameters for a given structure. And by structure, I'm talking about which variables we're tracking through space and or time. So in a traditional microphysics scheme, this might look something like the mass concentration of small drops and big drops in a cloud. The additional component of structure is what kind of functional forms do these variables, temporal and spatial derivatives, take? So do we have something that's linearly dependent on temperature? Maybe we have a power law. The other element is parameters. So these are constant values that are used in a given parameterization structure's functions. So sometimes these are physical properties, like say the density of liquid water or surface gravitational acceleration. But often, especially for microphysics, these parameters are poorly constrained or just kind of completely lacking in physical meaning. So we don't really have an idea of how to constrain them. And both of these elements of parameterization design can contribute to errors related to parameterizations in climate models. But traditionally, it's difficult to characterize these structural and parametric errors rigorously and quantitatively, and also to untangle them to understand what's driven by parameter choice and what's driven by structure. And so today I want to talk mostly, or basically all about how we can improve parameter selection to make this more quantitative and to do more rigorous parameter estimation. But I just want to mention structure, as this is also very important, probably more important, and we're also thinking about that, which I'll touch on a little at the end. Okay, so the goal of what we're trying to do is, with this project I'm presenting now, is to do quantitative climate model parameter selection based on some kind of key metrics from some constraint source. So given parameters input into a climate model with a given parameterization structure, we want to maximize agreement as a function of these parameters, some kind of like key metrics that we care about and their uncertainties relative to some constraint source. So this could be a more complicated model. Sorry, is everything okay? This could be a more complicated model, or it could be observations or some mix of those two things. So Bayesian parameter inference is a desirable method to perform this quantitative parameter selection. However, it's too expensive to directly use Bayesian inference methods in climate models because we need to run the model, say, millions of times. Instead, what we do, building on work from Greg Alsasser and Marcus van Leeuwenhoek to tune the NASA GISS climate model, is to use machine learning to emulate how the climate model with its different parameter dependencies will produce these kind of key metrics that we want to use to constrain our model parameters and to do Bayesian inference using this emulator. And we train this emulator using a more limited number of runs of the climate model, more on the order of hundreds, with different parameter combinations. And so what we're using specifically here, that was kind of a general introduction, is a framework called BOSS, which can configure microphysics parameterizations via Bayesian inference. Another key element of BOSS, which I won't go into here, but I'll just reference, is that it's also very flexible structurally. So we can also test those structural components. And so the work I'll present here is looking at constraining 16 of these microphysics BOSS parameters in a large eddy simulation. So this is what you might think of as a cloud resolving model for those not familiar. And we're going to constrain these kind of parameters using a more complex spin microphysics scheme. And so specifically, the climate model we're using is CM1. We're using kind of a traditional microphysics parameterization setup with power laws for process rates and 4 variables. And the setup we're looking at here is a marine stratocumulus. Kind of the key metrics we're using to constrain our parameters with are different spatiotemporal averages of our domain at 6 different aerosol conditions. For our, in accounting for uncertainties, we consider both the emulator uncertainty and also dynamical variability. And for our ML emulator, we're using an ensemble of neural networks, specifically the RPNs that Aziz mentioned previously. And these are trained on 850 BOSS runs of this LES. And so if I kind of lost you in all those details, basically the idea is that we are trying to constrain 16 microphysics parameters in a cloud resolving model based on a much more detailed microphysics calculation that has about 20 times more variables and much more detailed process rate calculations. And so I will now show some results. So we can use the emulator to evaluate the BOSS parameter sets performances against the bin schemes. So here I'll just show kind of one of our key metrics, which is the average surface rain rate. And I'm showing it as a function of background aerosol mixing ratio. The black points are coming from the bin model, and the standard deviation is coming from dynamical variability, just the chaos of the dynamics evolving. And first, I can show you what a single output of our neural network ensemble looks like, so we can predict continuously across aerosol mixing ratios, and this solid line is showing the mean of our ensemble, and the shading is showing 1 standard deviation. And so these are all parameter combinations that are coming from our kind of prior guesses of what the parameters might look like. And we can kind of see that they're all over the place. Maybe they have vaguely the right functional shape, but they're clearly not hitting all the points. Now I can add in overlapping 500 different prior parameter sets. And we can see that they kind of span what the bin model is doing. And sorry, for context, this prior is coming from direct process rate fitting. But these prior parameters are not kind of agreeing with the bin metrics. In contrast, I can show our posterior parameter sets. So these are just 500 parameter combinations drawn after we've performed this machine learning enabled Bayesian inference. And we can see that our method is working, and we're finding parameter combinations that agree with the bin metrics. I'll just note that this is only kind of possible where it's structurally possible. If the model, if the parameterized model can't produce certain physical outcomes, it's not going to magically happen from different parameter combinations. And kind of lastly, what we'll look at is, so what I've shown you so far is all machine learning emulation. What happens when we actually put these parameter combinations back into the LES. And so here now I'm looking now as a function of time at the mean surface rain rate. And these different panels are showing different levels of background aerosol. Oops, wrong direction. So first we can look at the bin results. So the only thing that's different between these individual bin runs is just a different random number to initialize the simulations. And if we look at BOSS runs drawn from that posterior distribution, we can see that we're capturing the bin model results, even though we didn't actually use any of the time involving information to inform our constraints. And I can also look at some different outputs of the model. So now I'm still looking at panels showing increasing aerosol value, but now the y-axis is going to be the altitude, and the x-axis is showing the average liquid drop mass flux from sedimentation. And so again, we can see the different bin simulations and add the BOSS posterior runs. Again, we can see these are kind of agreeing with and spanning the uncertainty from the different more complicated model realizations. Okay, so to kind of wrap up the implications of what we can do with this work, I've shown that this framework can give us an automated procedure to quantitatively, based on quantitative metrics, tune our model. And so from this framework, we can characterize parametric error from these posterior parameter distributions. And we can also distinguish what is coming from parametric error, because we've explored a very broad parameter space rigorously. And that will allow us to distinguish parametric error from structural error. So where we actually just need to change the fundamental assumptions of our parameterization rather than just choosing different parameter combinations. And with that, I'll kind of just look at what we're planning to do next, if I still have time. One step is, of course, in line with LEAP's goals, we actually want to put BOSS into global models or system models. So right now we're working with CESM and E3SM and constrain these microphysics parameters with actual observations. And so here I'm showing, or I guess I'll mention that our collaborators at DOE and NCAR have implemented BOSS into these models. And here I'm showing results of BOSS in E3SM. These results are from Paul and Ma. I'm plotting shortwave cloud radiative forcing for the non-climate scientists in the room. This is kind of like how shiny are clouds. And at the top, we can see what the observations look like. The middle panel is showing an E3SM standard microphysics run, and the bottom panel is showing BOSS. Just to be clear, these runs aren't tuned. So the fact that the BOSS run is much more in line with observations is just kind of a coincidence. But basically, we can see that when we put BOSS in the model, it's implemented, it's not doing crazy things. The other path that we're going to look at is to address this kind of structural component, staying in the LES framework or the cloud resolving framework that I mainly presented on, but we want to use Lagrangian microphysics, which are kind of a more realistic picture of microphysics than the bin scheme that I was showing before. And then finally, we kind of want to bring these two elements together to build a pipeline from the physical insights we can get at a cloud resolving scale and bring them to the global scale. And with that, I'll wrap up. I'll just kind of summarize the main chunk of the talk. Basically, it showed that machine learning enabled Bayesian parameter inference is a quantitative method to select parameters, characterize parametric uncertainty, and distinguish parametric and structural error in parameterizations. And I showed an example of its successful implementation for a cloud microphysics parameterization in LES, where we constrained 16 different parameters. And with that, I can take any questions. Thank you for bearing with the technical difficulties.
Any questions? Are you starting with the particular sentence, particular sentence?
I think that's one. This is probably a very hard question, but something that I think about it. I'm wondering if you have thoughts about it. But the challenge of trying to do this in a global model where now your parameterized microphysics is interacting with parameterized convection, parameterized cloud. How are you thinking about tackling that?
Yeah, I think that's a really good question and like kind of a grounding question. I think that's one of the reasons that we really want to do a lot of exploration in something like an LES where we can actually resolve the cloud macrophysics. I think another element is, yeah, we're gonna have to talk to the people, like these microphysics parameterizations also have to couple with different modules that are traditionally not developed by the same people. So like, yeah, convection, radiation, I think will be really important. And so I think our idea is to do a lot of structural probing in LES, look at different kind of cases where we can use model results as kind of a benchmark, get kind of realistic parameter combination ideas, and then kind of look at what happens in the global model.
That was just so lovely and clear that it excited a whole bunch of questions for me. So one would be sort of a technical question, or a couple, they're all sort of technical, I guess. One of them is that you have the LES, which runs with the bin microphysics, but you don't sample the trajectory in time, you sample individual snapshots. And this is how you're getting.
So right now, so in practice, the method is general. We can choose whatever kind of constraint metrics we want to use. The issue with using like single moments in time is, especially when it's like actually precipitating, the dynamical variability is quite significant. And so especially, it is a bit of an easier task if we're like using the same LES just with different microphysics schemes. So when we look at, or looking kind of at right now we're just using kind of averaging the last 2 hours of the domain and looking at like very coarse vertical profiles, or that kind of of the metrics we've tested so far, the vertical constraint has been the strongest. And part of that is we looked at kind of distributions of parameters across, sorry, not parameters, of outputs, like across time. And the structural uncertainty kind of is dwarfing like what we can kind of do with the parameters. But yeah, I don't know if that answers your.
No, it does. And then just as a follow-on, does BOSS, when you run BOSS with different sets of parameters, are you also redoing the dynamics, or are you just piggybacking on the existing dynamics?
Yeah, so actually doing piggybacking is something we're thinking about right now. Everything is done independently, so the dynamics are completely separate. They're not tied to like a bin runs dynamics.
And then finally, when you do an implementation in a GCM, what you get out of this process, as I understand it, is a joint distribution of parameters.
Mm-hmm.
Do you implement that in the GCM, or do you implement the central estimate, or how do you do?
Yeah, I think that's it. I think that's a good question, and I think something that Marcus and Greg are pushing for is to not just, and I think that's something that becomes possible when you have an automated procedure to do tuning, is you can get a bunch of different parameter combinations that give you like equally viable model outputs, and then internally to your model you can assess like, okay, this is like kind of for CESM version 3, whatever, we can kind of assess the internal parametric uncertainty because we can come up with different combinations of parameters. How to choose like a single parameter set is probably something that I imagine would become something of an engineering task for like a really CMIP scale model, because they have certain metrics that they really care about more than maybe like we as more general practitioners would care.
I have a question online. Great talk. Do the LES runs include both open and closed cell stratocumulus? Does BOSS perform similarly for both cases?
Yeah, so here we are using the same kind of dynamical forcings for all the runs. We're just changing the aerosol concentration, which gives you different precipitation outcomes, but doesn't really lead to, at least in the period we're looking at, like transitions between open and closed cells. What I have been working on recently is also including as parameter inputs variables that characterize the temperature profile and water vapor profile. And in those cases, we do see like the emergence of different cloud morphologies like open and closed cell stratocumulus. And we haven't fully run the emulated results back through the LES yet. So just to clarify, but at least from the parameter constraint part, we're seeing quite good matches across these different dynamical realizations. Whether that holds if we go to something like cumulus instead of just different types of stratocumulus, I'm a little bit more pessimistic about, but yeah, it's we have some indication that it could generalize at least a little bit.
Yeah, great talk. I had kind of two related questions. I mean, the first one is when you actually fit BOSS, especially in the LES case, so then it's fully online, right? Then you're plugging BOSS and replacing the bin microphysics, and then comparing that to the bin LES run, right?
So we're not doing any kind of like training online, but the evaluation is done based on the total evolution of
Right.
the
So it works really well, right?
yeah, and so one of the things that we had to do was change how we like set our kind of like initial guess, like how do we set up these like parameter combinations that we actually run through the model, and we use kind of like direct fitting of not temporally evolving process rates to do that, and then kind of like decorrelate the parameter combination so that we can sample effectively.
But in a sense, I mean, maybe that's touching on as his talk as well, is that it's humbling at the same time for people doing machine learning based emulation, right? Because that seems to work really well. And kind of under the hood, what you have is you have some state, right? You also have like parameter that are controlling the evolution of the system, right? But that seems to be evolving in the right direction, seems to be relatively stable, right? And that's something we are typically struggling with, right? When we have a machine learning based emulation, right? So that physical constraints and having just a few parameters seems to be really helping you, like having this long time scale dynamics correct, right? So that seems to be kind of hitting the right spot, you know. Yeah.
Yeah, I guess like one advantage of using the machine learning kind of like offline and not in the model is that it's kind of, we can kind of build in a lot of checks and limiters into the like physical parameterization, and we just need to tune a few parameters. I guess in theory you could tune a like machine learning approach parameters like via this method, but I think it would probably be quite computationally intractable.
And maybe just last question related to that is, and that's related to the earlier question, is that implicitly what you're doing again is you have some state variable, you know, like moisture, temperature, and so on and so forth. You have some parameters and then you have some evolution, right? But when you talk about the emulator, I think we need to, as a community, to be careful as to what we call emulator, right? It could be a long-term statistics, some of the long-term statistics. So that's really the work that Greg and Marcus have been doing. So you want to match, for instance, your annual values of, say, top of the atmosphere radiation or something like that. But at your scale, it's a little bit different, right? You have the dynamics, like the temporal evolution, and the parameters as well, right? And those two could be quite different, right? And for the emulation, for instance, especially if you integrate over space, related to the earlier question, I mean, you could get the right answer for very wrong reasons, right? So because you're basically integrating over the entire state space, right?
You mean in like how we're pulling out the metrics to constrain based on?
Yeah, if you're emulating it, but integrating, say, over space or over time, you could be integrating over many, many different conditions. And yes, you could get the right answer, so the right mean value, but maybe for very different reasons, you know, underneath, right? So
Yeah.
worrisome.
Yeah, I agree that that's like a big area of concern. What I would just say, like practically, is this is clearly happening in our climate models already, arguably to a worse extent because we're not really. I think this is kind of where the structural element comes in, right? Like we can get maybe the right means, but we can't get the distributions correct, and this is kind of persistent across many different generations of models and many different modeling centers models. I think like that's kind of indicative that we really need to think much more critically and much more quantitatively about the structure of our parameterizations. And I think one thing that's really limited our ability to do that is kind of this tuning problem, right? People will adjust the structure of the parameterization, it behaves worse, and the kind of thing is, well, is it because the structure actually isn't better, or is it because we didn't like hand tune the model for 6 months? And it's really hard to compare different structures. That's kind of where I see this methodology really being helpful. I think the problem actually is really driven by the structure. And so yes, we have to be kind of careful in how we choose to, like what we're choosing to constrain on. But I think we can also now show like, okay, we can match the mean, we can't match this distribution. That's showing us we have structural error that we have to address.
I could respond. I think this is like an interesting question overall of like observations and the information in observations. And yeah, you just take like an average, like whatever liquid water content as a single metric, or you could take like every point. You know, you have these two extremes of like taking every point in space and time, or like the most basic average that you can do. And I think either of them is bad. There's some optimum in the middle. And I haven't heard anybody come up with like a principled or reasoned or systematic way of actually finding out where in that space is where you want to go. And then I think there is the additional complication of what Kait's saying, that there is the structural uncertainty. So if you're estimating parameters, well, you're not estimating the structure at the same time. So I think that has to factor into how big of a hammer are you hitting your model parameters with, if you still have to structure them. So there's a lot of questions there, I think, that are actually pretty cool science questions to figure out.
Thanks so much. So with that, thanks so much, Kate, and Aziz as well for the nice talks. Yeah.